Hello. So today we will discuss another intuitive way of formulating the SVM optimization problem of getting the hyperplane with the maximum margin. So that is our aim of getting a classifier with as big a margin as possible. So we have this sample set with three positive samples and three negative samples. And we have this H0 is our decision boundary, and H1 and H2 are the gutters on both sides of this boundary. So we just recall that the distance of a point x0, y0 from a line is given by this uh, computation. So the distance between H0 and H1, that is this distance is given by, here the dot product of W and X is equivalent to what we had written here, because X we would realize would be having two components, X1 and X2. This is our X. And similarly, the W would be having two components, W1, W2. Since we are talking of 2D space here. And this is the norm of W. So it is the distance between H0, H1 is 1 by norm of W. Now, the same thing would be true for the distance between H0 and H2. So we are looking at both the distances from H0 towards H1, which is the positive side samples, and H0 to H2, which is belongs to the negative side, negative samples. So both being 1 by norm W, the total distance between H1 and H2 is 2 by norm of W. And this is the quantity which we aim to maximize. So the main idea of SVM is to choose the hyperplane defined by W and B that maximizes this margin. This is the margin. And if we call this delta H star as the margin for hyperplane Hx equal to 0, Hs equal to 0 is nothing but this Wx plus B equal to 0. This is our hypothesis, Wx plus B. Then the goal is to find the optimal hyperplane, which we represent as H star, which you get as that H which maximizes del H star, or that combination of W and B, the weights and the bias, which maximizes this quantity 1 by norm of W. So the optimization problem is to maximize 1 by norm W or to minimize W, because it's the same thing. Minimize W such that these are the constraints, yi Wtxi plus B is greater than equal to 1. Now we write an equivalent minimization formulation of the above as follows. At minimize over parameters W and B, half of W squared, norm W squared. So you wanted to minimize W. So equivalent formulation can be minimize W squared. And the linear constraints are given as follows: Wi Wtxi plus B. So this is actually a dot product. Is B greater than equal to 1 for all the n samples. So this is a constraint optimization problem. This optimization constrained by this with n linear constraints, because we are assuming that there are n samples. You can recall from our previous discussions where we spoke about the functional margin and geometric margin, and we finally got the SVM decision boundary defined as the same thing as which we have written now, because when you incorporate Wi equal to 1, yi Wtx be greater than equal to 1, and for this, writing this, the product less than equal to minus 1 is the same as incorporating both together under this linear constraint. This is for all. I equal to 1 to n. So we have written down the SVM optimization problem from an intuitive approach, thinking of the hyperplane and its surrounding the wide streets and how the distance calculation is made, and we end up with this optimization problem. The next step would be to obtain the dual formulation, because we do not want to solve this problem using the standard optimization techniques. We want to take it further for some intuitive insights into the SVM, the support vector machine classifier. So thank you for watching.